In my talk today, I'll tell you about my recent work on the strongly correlated phenomena in twisted bilayer graphene. In this work, we used DMFT with the numerical renormalization group NRG impurity solver to characterize the gap opening of mechanisms in this interesting system. By considering the partial symmetry breaking associated with the spontaneous valley-orbital ordering, as well as effective Hund interaction induced by the dynamic Jahn-Taylor effect, we could identify many interesting gapped phases in the system. And also, we found that the Hundness coming out of this effective Hund interaction can explain some enhancement of the pairing susceptibilities near the filling factor 2. So in this talk, I'll mostly focus on the contents also shown in this our recent preprint, but also I'll show some unpublished data which we are preparing as a separate manuscript. So it is quite honorable for me to give a talk in this symposium because actually we are really influenced by the earlier talks almost 1 year ago. So I was in the audience about the works on using DMFT to study the twisted bilayer graphene, and roughly 1 year later, now I'm talking about some updates. So before going into details, let me give you just a quick introduction to the twisted bilayer graphene, well, mostly magic angle. So we have 2 sheets of graphene, which is rotated by about 1 degree. And then there is a moire pattern having the AA stacking regions forming a triangular lattice, and AB and BA forming a honeycomb-like situation. And then if we neglect the hybridization between the 2 layers, then we can think it as just independent 2 layers, which whose Brownian zones are rotated by this twisting angle. And also the dispersion will be given by the simple superposition of 2 directons near this K points. But by turning on the hybridization, then these 2 directons hybridize, forming a flat band within the Brownian zone. So this physics was first, say, predicted by Bistritzer and MacDonald in 2011. And then experimentally, the MIT group found the interesting physics by realizing this material. So namely, they found the correlated insulator phases at filling factor ±2, and also superconducting phases nearby them. So this is a schematic figure, but this one agrees well with their experimental data, and also many other experiments have reproduced that. And out of this phase diagram, actually the question from my side is that here the gaps mostly open near U ±2 compared to the other fillings. Some experiments report that, but the gap opening is weaker or often not observed at all. And also the question was how do the gaps open, because they simply code it as correlated insulator, neither a mode insulator or whatever. So just they don't know why the gaps open. And also an interesting question, as always, is what will be the relation between the correlated insulating phase and the superconducting phases? So dynamical mean field theory is surely the way to go to give the first correlated answer to that. So I think everybody here in the audience is the expert in DMFT. So I'll just give you a quick introduction. So DMFT maps an interacting lattice onto an effective impurity model, where we take a lattice site and put it as the interacting impurity and map the rest of the lattice onto a non-interacting back. And the correlation effect throughout the lattice is now encoded in the omega dependence of the hybridization function that describes the coupling between the impurity and the back. And it involves the single approximation that the self-reference is local, in other words, momentum dependent. So in the real space, now the self-reference is decoupled from this canonical delta. And being mapped onto the impurity model, now, in my view, DMFT basically describes the lattice system as a self-consistent Kondo effect. So impurity has fluctuations like spin, and the best screens that. So this is the cartoon picture for the minimal Kondo effect. And then also it is a kind of, say, mean field theory, so we should obtain the self-consistent solution. So it can be reached by solving the impurity model iteratively using a so-called impurity solver that takes the hybridization function as the input and the self-energy as the output. Then basically it becomes just a matter of choosing the proper impurity solver to get the good, accurate solution. So there are many impurity solvers in the market, and I am using the numerical renormalization group, which was originally invented by Kenneth Wilson to solve the Kondo problem. So this is again the quick overview of the NRG. So I start with discretizing the bass using the logarithmic energy grid. And then by mapping it onto the chain, which is so-called the Wilson chain. So I have a specific 1D system whose Hoping amplitudes scales logarithmically or exponentially as the index of chain site. And lambda is just a hyperparameter. We typically choose between some value larger than 1, smaller than 8 or 10. Here in this board, we choose 4. And then by using this scaling structure, then by using the iterative diagonalization, we can construct the complete basis of many-body energized states that also have this logarithmic structure. And then each state can be now represented as their matrix product state. And then the correlation functions can be evaluated by using the spectral representations. So for 2-point cases, it can be obtained by evaluating this kind of diagrams, and they can be generalized also to the multi-point cases. But I'll basically only use the 2-point calculations for this talk. And there are several strengths of the NRG. First, it is the real frequency solver, so we do not need the energy continuation. And also because of this logarithmic structure, we can cover a wide range of magnitudes. So starting from the bare energy scales to the much lower energy scales that can be even accessed by experiment. And also we can deal with general parameters because it's a Hamiltonian-based system, so there's no sign problem. So in recent years, I have developed the code package for this NRG and its DMFT impurity solver application. And then with this, we could solve many interesting problems. So then coming back to the twist Bilayer graphene, actually previously for I think the first several years after this experimental, say, booming from 2019, it was not trivial to study this interesting material using DMFT because it was hard to find a proper lattice description because there was a problem so-called the Wannier obstruction because the flat band has some topological nature and they could not be compactly described using some small set of Wannier wave functions. But in this work by my colleagues, Seung and Andre Verbeek, they found the lead idea. Well, of course, the some other groups like C-Dice group, they also made major contributions. But here I take their version. So here in the AA resonance that form the triangular lattice, electrons are localized, which we call F orbitals, taking the analog from heavy fermion physics. And also there are C bands, which are associated with this honeycomb lattice that form that has a topological GF And then here, so it just if we do the number counting, so this is the surely electronic system. So we have spin 1/2, and also this is the graphene-based system. So we have K and K prime as some pseudo spin degrees of freedom. And per spin per valley, we have 2 F orbitals that form lattice and 4 C bands that form continuum. So this is also continuum, means that there is no Bragg zone. Basically, the K space is theoretically infinite. And then the Song and Bernvig have obtained this interaction term by projecting the original Coulomb interaction onto the binary wave functions. So there are 5 terms. The first one, the largest one, is the on-site F interaction, which is SU8 Hubbard, and we will treat it. We can treat it with the DMFT dynamically. On the other hand, there are some other non-local interactions or some interactions involving C bands, and then they can be treated using static mean field like Hartree-Fock. Some earlier works, including the works presented in this symposium last year. There were some works using DMFT with the CTQMC Monte Carlo impurity solver targeting the O8 spin valley orbital system. So this 8 corresponding to the range of the filling factor from -4 to the 4. And so here I took the figure from this paper, in this PRX paper, where the authors plot the quasi-particle weight and also spectral function height. And here we see that if we compare this, for example, especially the red curve from the numerical 2 and numerical 1, actually here it is smaller. So it means that the numerical 1 is more insulating than numerical 2. But as I said in experiments, numerical 2 is mostly insulating compared to the other fillings. So it means that we need some more ingredients to understand the stronger insulating behaviors at U ± 2. And also there was a detailed discussion on the type of the gaps, but there was no, say, conclusive answer for that. And let me just mention as well that there was also some study using the first principles description of this material. But as far as I understand, also they got the idea of this heavy fermion type description of the system. And then also the conclusion is quite similar. So as I said, we need the new ingredients, and here we have actually the 2. So the first one is the downfolding the original full 8 spin valley orbital model onto the half based on the partial symmetric breaking at the numerical 0. In other words, charge neutral point. So it is based on the observation that if we consider a system at numerical 0, and then the hybridization between F and C becomes minimal because the C is a Jahn, so it has a vanishing density of state. So basically the Kondo screening is suppressed and the RKKY wins. So the TBG is susceptible to the value orbital ordering. So if we consider a finite nu as the situation that we first fill up the electrons up to half the charge neutrality point, and this half-filling system is now ordered, and we add extra electrons, basically excess electrons to reach this new. So in this work, we consider the three different valley-orbital ordering scenarios, which are the valley polarized VP and Kramers intervalley coherent KLVC, and also recently highlighted ordering, namely the time-reversalsymmetric intervalley coherent TIVC. So as you see, the names are very long. So I will simply later on just mention the abbreviations. And then here we also consider just this active space as just being paramagnetic, and then this is the part we will use DMFT to get the solutions. And then, of course, this is the case when U is larger than 0, particle doped, but for negative nu case, we can simply get the solution by doing the particle transformation of this. And the other one is the effective Hund retractions coming out of dynamical Jahn-Teller effect, which is reminiscent of polarized. So in this material, actually there are two effective Hund retractions. One is a spin anti-Hund, but actually this form looks a little bit different from the standard Hund form, because now here +1 and -1 indicate the orbital indices, because there are effectively two orbitals in this system. And then also there is a orbital-angularmomentum Hund term. And this strength of the spin anti-Hund and orbital-angularmomentum Hund depend on the choice of the ordering. So this is the quick table. And roughly speaking, the VP and TIVC are similar in that the JS is much larger than JL. On the other hand, the KLVC is the other way around. And before showing our numerical results, yeah.
So you mentioned Jahn-Teller, right? So
yeah.
What Jahn-Teller modes are we talking about here?
So regarding the phonon degrees of freedom, actually in this paper, so my collaborators have derived the form, and here they consider all phonons, say acoustic or optical, and the gamma and K, they put them everything. So that's how they obtain this effective Hamiltonian.
Mm-hmm. But these are phonons of the graphene sheet, right? That's what you're saying.
Yes, yes. So they have actually quite high energies. So it is also demonstrated in the recent, I think, Nature paper, experiment paper. So they found the phonon band that are quite at high energies. So that's how also we treat this effective interaction as the non-retarded one. So of course it's a approximation.
The word Jahn-Teller to me evocates the local phonon associated with a local entity, like for example in a perovskite deforming the octahedron in a specific way, the Jahn-Teller mode, or in a in a buckyball that you mentioned.
Mm-hmm.
But here we just have one carbon atom per side, right? So what is the local entity we are talking about?
So you can view the this Moiré unit cell as a big version of a buckyball. Yeah, so it's actually much larger.
Okay, so it's this object that has a Jahn-Teller mode. Okay, got it.
Mm-hmm. Yeah. Mm-hmm. All right. So let me go back to the this. So before showing our numerical results, I'll explain how we classify the different gap opening scenarios. So in DMFT, the F orbitals, Green's, and spectral functions are given like this. So first, the Green's function, it has just a simple form. In the denominator, we have self energy and also the hybridization between the F orbital and the rest of the system. So please note that this is the rest of system. It means that including the C band as well as the other F orbitals. And then this is nothing but taking the imaginary part of this Green's function. And then it means that the gap in the F orbital means that this spectral function at omega 0 at Fermi level is small. And to get this, there are actually only a few cases. The first case is that the numerator is small. And here they have the same sign. They should be both negative. So they both should be small. And we call this scenario as the hybridization gap, in short HG, because it is mostly noticeable by having this small hybridization function, because this one can be reached if it were, for example, the Fermi liquid. And the other case is that the denominator is large. It can be driven by this self-energy part. And here I just combine mu with the sigma, because this one can be absorbed to the sigma by just redefining the definition of the self-energy, by including the quadratic shift. Here we call this case as the orbital selecting mode, OSM, if there is a pole, sigma pole, self-energy pole near omega 0. So basically the the peak of the sigma double prime. And also we found that this can be huge, especially the rear part can be huge, even if there is no self-energy pole. So we call this case as OSM prime, based on its similarity to OSM, but it's a bit different. And also it's prime because the mostly driven by this prime part. And the other one is, of course, the delta. If the magnitude of delta is large, then this one can be also small. And this is a well-known case of the conduit insulator. And then as I just classified, some can coexist. Basically, the HG and OSM, they can coexist because there's no contradiction. Actually, only the contradiction is OSM versus OSM prime because of the definition. All right, so this is our phase diagram. So here we only focus on the lowest temperature we could reach, which is the 10 to the minus 6 millielectron volt. But we don't call it a zero temperature for the reason I will tell you in the next slide. And so there are actually 5 cases. Even though we consider 3 orderings and the electron-phonon coupling, electron-phonon coupling, and without it, but when we turn off electron-phonon coupling or the effective Hund interactions coming out of dynamical Jahn-Teller effect, then after downfolding, the effective Hamiltonian between the VP and KVC cases are the same. So there are 5 cases. And also here we show this colored shades as the gap opening cases, and the white cases are the gapless. And also we plot the F contribution to the entropy per Moore unit cell as these solid line curves. All right, so it looks a bit complicated, but I'll just go through step by step. So first, a noticeable difference by turning on the electron-phonon coupling, or again, dynamical Jahn-Teller effect, is that it enhances gaps near numerical 2. So this sky blue regions just show up by turning on electron-phonon coupling. And how can you understand? Well, actually, there are lessons from Hund metals because the Hundness favors insulators at half filling. So as shown in this seminal review paper, by turning on the Hund's J, the critical U at half-field decreases significantly. So we can just take the analog, and also we did the analysis of the atomic gap, and basically we got the same result. But another interesting thing is that the partial symmetry breaking associated with the valley-orbital ordering is important, because without this, the half-filling, where the gap opening is enhanced, will be equal 0. But by having this partial symmetry breaking, now the half-filling point is shifted to the equal 2. So that's how this gap opening is enhanced at equal 2. And the other interesting features are the large spin value orbital moments can be seen by this large value of SF. And then here, except for this KIVC at the equal 3, all the other cases have large moments. So they may explain the symmetry breaking states in experiments. So our explanation is like this. So they have large moments, and then these moments can talk to each other via a very flat band. So the interaction may be almost ferromagnetic. Archaic interaction is ferromagnetic. So then it might explain the symmetry breaking orderings in these Felix. The other one is this, which is also quite interesting. So here we see that the SF from DMFT side, or excess electron or active subspace, is basically 0. It means that there is no extra moment from DMFT, so it just reveals the underlying TIVC order, as also observed in the recent STM measurement. So it nicely reconciles experimental observation with theory. And let me also mention that maybe some of you might already have noticed, I didn't include the condo insulator case. I actually didn't even introduce the abbreviation, because in our case, it doesn't show up, because the condo insulator involves the divergence of the hybridization function. But in this system, because the C-band is just a Dirac band, so the hybridization is typically small near omega 0. So that is the reason why we don't see the divergence of the hybridization function. So this is the thing. And then if we look at the other white widths, you might also see that the SF is not 0, say log 1. Actually, there's a slight up and down, and it looks a bit different. It's also here, as you see, there's some quite enhancement, but I reclassify as the gamblist. So it just shows that it is not Fermi liquid. If it were Fermi liquid, then the SF should be 0. And also we checked that this FRG, the major part, is not small at all. In many cases, they are quite noticeable. And also by using the NRG, then we can use the energy flow diagram as basically the RG flow, and found that most of these points do not reach the Fermi liquid fixed point. So our conclusion is that many of them, actually almost all of them, are in coherent metals with a very small coherence scale, even smaller than our choice of the temperature. So that's why I didn't say that it is a 0 temperature, because maybe there might be some further extreme low temperature physics, but I think it is, of course, not accessible by experiment. And then also one important remark is that the quasi-particle weight, Z, cannot be defined because it's not Fermi liquid, and even it cannot be computed, because we try to actually fit the real part of self energy just to take the slope to obtain the quasi-particle weight. But it turns out they have some structure, and they are, so it was really tricky to obtain the quasi-particle weight in many data points. And just before moving on to the next part, also we made the comparison with our data regarding the chemical potential and the filling factor to the data in the recent PRX paper. So actually these curves almost lie on top of each other regardless of electron-phonon coupling and the valley-orbital ordering, and that they mostly agree with this published result. Only this discrepancy is this, but I think first this small difference here might be and also here might be related to the different system temperature. So we consider much lower temperature than this paper used. All right, and then I'll go to the basically the one of the key results, another key result in our paper. So which is the explanation of the pseudogap at the nucleus 2. So this large box shows the AF F spectral function at the large scale, and the inset zooms into the low energy window. And the different line curves indicate the different ordering. Of course, here the EPC, electron-phonon coupling, is all turned on. And then also there are some markers. Okay, these markers, sorry, before going to the markers, so here we basically see the pseudogap is not a hard gap. And then this gap is accompanied with the side peaks. And this form shape is basically quite similar to the experimental observation using STM. So they also found the pseudogap with side peaks. And then also these markers now indicate the energy differences of atomic energy levels of a half-filled impurity. So here we have actually the three different energy values that are just split by effective Hund interactions. If there were no electron-phonon coupling, then they would be all degenerate. But by having this effective Hund, they now have differences. And then basically we see that these markers align with the side peak positions. So it means that this pseudogap with side peaks is the manifestation of Hundness induced by electron-phonon coupling. Okay, so to see to understand more detail, we also study the dynamical susceptibilities for several different excitations. So again, the EPC is all turned on, and this is a VP case, and the KIVC and TIVC. They are quite similar, especially VP and TIVC are similar, and the KIVC is a little bit different because in VP and TIVC, the atomic ground state is singlet, so having the orbital 0 and spin 0. On the other hand, in KIVC, the atomic ground state is the twofold degenerate, so orbital is plus minus 2, and it is spin singlet. And let me note that here the SU2 spin symmetry is there, so it is SU2 spin quantum number, while this L is just U1 symmetric quantum number. And then, so having this ground state, and then we found that the dominant fluctuations for all cases is first the orbital momentum flip, which changes this small L. And for VP and TIVC, the staggered spin excitation is also dominant, while for KIVC, the orbital spin flip is also there. So we have these markers, and actually these markers are at the same positions as I showed in the last slide, and so it means that these susceptibilities really explain the side peaks of the pseudogap. And also we computed pairing susceptibilities. Here I only show the static part, so namely the real part at omega 0. And then also again we consider 5 different cases. And now we consider the different symmetries of the electron pairs. Of course, let me note that here we only focus on the normal state. So the U1 charge symmetry is there. But still, we see that by turning on the electron-phonon coupling, so so if we just start from the electron-phonon, the case without electron-phonon coupling, the black and the gray curve, and by turning on, we go to the colorful lines, and depending on the symmetries, pair susceptibilities are really enhanced. Some other ones are suppressed. And actually, the enhanced ones are really associated with the atomic configuration, which is favored by this effective Hund interactions. So basically, it reflects the f orbital ground state. And this range is about from 1.7 to 2.9. And this one agrees well with the first observation in the experiments. So there are superconducting domes over a quite similar range. So I think probably this kind of pairing fluctuations favored by Hund couplings might be a precursor to the superconducting domes in the experiment.
Seung-Sup,
So here,
you're getting to the end. That's good because you've already entered question time. Go ahead.
Yeah, all right. So basically, this is the last slide. So in this work, we characterize the gap opening mechanisms and found that the effective Hund from electron-phonon coupling, or a more professional term, dynamical Jahn-Teller effect, and then also partial symmetry breaking, valley-orbital ordering. By having that, we can explain the robust pseudogap opening at unical plus mass 2 as the orbital selective mode phase. And also the Hund coupling enhances the pairing susceptibilities, so which might be explain this superconductivity. So here I show the figures taken from also this paper. Actually, just some data points were updated after some new calculations. So this figure is a little bit different from those here. So we'll also update the preprint sooner or later. And also we are preparing another accompanying paper for the susceptibility and the metallic phase analysis. So this work was done by my collaborators, the Seung-Yan and Bum-Jun in my group, and also Gongdong and Zida at Peking University. So let me just take just 5 seconds for a quick advertisement. So in my group, the PhD and postdoc positions are available. So if you're interested, please contact me. Yeah, thank you very much.
Thank you.
Thank you, Seung-Sup. Okay, so now we're going to take questions. First, Antoine, see your hand is raised.
Yeah, thank you for the nice talk, Seung-Sup. I have a couple of questions. The first one is technical. So I didn't quite understand what allowed you this breakthrough applying energy to this rather heavy problem. If I'm not mistaken, there are 8 correlated degrees of freedom per sites, right? 2 times 2 times 2. And so what allows you to treat this with energy? That's the first question. The second question is about particle hole symmetry. So I noticed that your results are not symmetric between, filling fraction 2 and filling fraction, on either side, like 1 and 3, right? A side of 2. So that must be because you start from a Hamiltonian, which does contain symmetry breaking, particle hole symmetry breaking terms, which is different from the work of Gautam et al. That you mentioned. So can you explain that as well?
All right. So yeah, thank you for the nice questions. So yeah, as you say, the energy's commutation cost will be very large if you consider 8 spin orbitals. But here we actually fix the half of the freedom. So the active subspace is just a 4 spin orbital. So that's how we could just solve the problem. And then the other question is the particle symmetry. Yes, original THF model has particle symmetry. So we just basically respect that. But of course, in the real material, that symmetry is broken. So that can be, I think, incorporated by updating the some Hamiltonian, basically this downfolded Hamiltonian. So I think it may be possible, but I think we didn't do it yet.
But the results you showed are not particular symmetric, right?
Yes. So it is not particle symmetry, yes, in the end, because the this symmetry breaking breaks that. So if we just extrapolate, okay, so we have the data point which we didn't show. So at mu equals 0, the mu should go to 0, but we see some shift. So that is essentially the artifact of the this downfolding. So I think this downfolding works better if we look at the some larger filling, larger dopings, rather than the close to half charge neutral point. So I think yes. So we have a downfolding, which might be an artifact, but anyway, to look at the larger doping, I think it would be okay.
Yeah.
Okay, thank you very much. Gautam?
Hey, thanks for the great talk and impressive results. So I have a further question about the downfolding. So if I understand correctly, you break a symmetry at the charge neutrality point. So 4 flavors occupied, 4 are not occupied. And then your active subspace is here, right? So then you dope, and then that's your active subspace. What I haven't quite understood is, how does this let you study the ordered state at nu equals 2, for example, right? How would it give you information on the IVC state at nu equals 2?
Yeah, so, all right. Yes, so here. So this the whole figure is about active subspace, which has no order. So we only obtain the parametric solutions or symmetric solutions. So for example, here SF is very flat, it's really almost 0 up to our calculation precision. And means that in the active subspace, there is no moments. So it is like a 2-stage situation. So there is the underlying TIVC order, as we just fixed as the hyperparameter. And there is that kind of TIVC order. And on top of this, there is just the plain paramagnetic active electrons. So that's our answer why the experimentalists observed the TIVC orders in this situation. So it is not all the electrons are ordered. The lower filling electrons are ordered, while the active electrons are not ordered.
Okay, I see. But don't we expect that at nu equals 2, you would have 6 flavors occupied and 2 not occupied? Just experimentally?
Yeah. Experimentally, yeah. So they just did looked at the nu equal 2, and then they just mapped out the STM phase the phase map, and then they concluded that that one is consistent with TIVC. But of course, there were some variants of TIVC. But so for example, if one doesn't use if one only uses Hartree-Fock, there is another, say, possible scenario, which is called the TIVC times quantum spin hole. But actually, the quantum spin hole scenario is really negated by this pseudogap, because my colleagues just did the calculation, and they found that quantum spin hole cannot explain this pseudogap with the side peaks. In any case, this kind of pseudogap mostly requires correlations. So I think the Hartree-Fock cannot explain that.
So there's two hands, but unfortunately, I think we have time for only one question. Next one was Luca.
Yeah, thanks. Thanks for the talk. What I didn't get is, maybe you just said it again, but what lets you take the n equal 2 as half filling? Because you say that you expect this gap to be larger.
Yes. So here, because again, let me go to this thing. So here we just fix the degrees of freedom here, and the active subspace just ranges from 0 to 4. So then these active electrons only know their effective downfolded Hamiltonian. So that's how the numerical 2 becomes the half filling. So there is no magic, just the our application of the downfolding.
Okay.